So let's now take a look at the last section of chapter 1. We did our best to give an introduction to 1.3 last time. And so now we're going to transition from that into 1.4. And so in 1.3, they defined all 6 trigonometric functions. And last time I just had us look at the first 2 of those, the sine and the cosine. And then I said, we'll move on to the other ones later. And actually what I'm going to do is I'm going to use what they start with in 1.4, these reciprocal identities here. I'm going to use those to help us get a better idea or approach to defining the other 4 trigonometric functions using the sine and the cosine. So then after that, we'll talk about these trig functions, their signs and their ranges, which we looked a little bit at. And then these things called Pythagorean identities, or also quotient identities. And that's our goal for this section. That'll finish up the chapter. So just while I've got a little bit of blank space on my screen here, we looked at the idea of something called the sine function of an angle theta and the cosine function of an angle theta to transition from last time. And my suggestion for this was a little bit different than what the book gave us, but ends up being the sort of equivalent. That if we have an angle theta where the vertex is at the origin and the initial side is the right pointing x-axis, and the terminal side is a ray from the origin sticking out, and we have a unit circle here. So I'm going to put a 1 here, meaning that that radial length is means this is a unit circle. Then I define sine of this angle theta to be the y value of that point. And I define cosine of that angle to be the x value of that point, which you can visualize those, so at least their size, on a little right triangle stuck in the middle there. And so if this point, if the x value is just cosine theta, then I can write the coordinates of that point by saying that's going to be cosine theta. And I can write the y value of that point by saying that's going to be sine theta. And then we looked at different ways where if we knew a point on a circle, you could evaluate the function for different angles. The nicest way, as we were just seeing in some of those example problems we just looked at, is that if the y value of the point is the sine of the angle, then if the angle is 90 degrees and your point is up here on the top, because that's where a 90-degree angle would be, pointing up at the top, well, then we know the coordinates of that point are 0 and 1. And that means sine of 90 degrees would be 1 and cosine of 90 degrees would be 0. And that we can look at other simple points around the circle, but that in general, these 2 functions are just giving you those x and y values for any point anywhere around on the unit circle at a particular angle of theta. All right, so we will be working with this tons and tons and tons, lots and lots and lots. So we will hopefully warm up to these functions and get used to them. But we now want to define functions based on these 2. Once we get these 2 in place like this, then there are going to be 4 other trigonometric functions that can be defined using these 2. And so they do that with an identity on the next page. They actually define them in the earlier section, but I like to best first start thinking about them using these identities. So the first additional function, so here's sine, here's cosine, and our third trigonometric function is called tangent, or tan of theta. And so the tangent of theta, I'm going to write in an extra step here to expand what they're doing. The tangent of theta can simply be thought of as the sine function's result divided by the cosine function's result. So tan theta is equal to sine of theta divided by cosine of theta. So if you already have a way to figure out what sine and cosine are, then to figure out tangent, you would just divide the sine answer by the cosine answer. So for example, if I go back up here to our little circle, if I had an angle, we'll say down here, and let's say that that angle, I'm going to do the opposite direction way in counterclockwise direction, this way. That means in this case, my theta is going to turn out to be negative 45 degrees. So if I have this angle down here, that means I'll have a point on the unit circle there. And I have a y value and an x value of that point. So I could use some properties of the Pythagorean theorem. I know my diagonal is 1 because this is a unit circle. And when I'm at 45 degrees, this is an isosceles right triangle where these two sides, the two legs are the same length. And if they're both the same length, you can solve that for x. You can basically say that x squared plus x squared equals 1. So the x ends up being the square root of 1/2. So that's the side of each of those lengths. So if I'm figuring out the sine, the cosine value, since that's the x value, the cosine value is the x value, which I know has length of square root of 1/2, and I know that's to the right. So that means the x value here is the square root of 1/2. Or if we rationalize the denominator, that would be root 2/2. So that means cosine of negative 45 degrees is equal to the square root of 2/2 or the square root of 1/2. That's what that function would give us for that particular angle. Similarly, the y value is of the exact same length, but it's down in the fourth quadrant below the x-axis. So that's going to be a negative y value. So that's negative square root of 1/2 or negative root 2/2. And so that means that when I take the sine of the angle, negative 45 degrees, that my calculator would tell me this, the definition tells me this, I'm going to get this number, which is negative square root of 2/2. The calculator will typically give you the decimal equivalent to that, but it'll give you that number to, the billionth place of accuracy or whatever you want. All right, so if I have an angle and I can find the sine and the cosine, well, we can now consider what would be the tangent of that angle, because I've just defined the tangent. And so tangent of an angle, based on this definition here, is the sine of the angle divided by the cosine of the angle. It's also a button on your calculator, so you could check your answer on your calculator or something like that as well. But what this would be is sine of negative 45 degrees divided by cosine of negative 45 degrees. And we were able to figure out both of those. So that means that it looks kind of ugly. I'd get what's called a complex fraction, but I'd get negative the square root of 2 divided by 2. That's the sine answer, all divided by positive the square root of 2/2. So sometimes when complicated fractions like this show up, we multiply on the top and bottom by the LCD to clear fractions. But in this case, the numbers are exactly the same number, just one's negative and one's positive. And when you divide a number by itself, you get 1. And when you divide a negative by a positive, you get a negative. So this just simplifies, lost my screen here, to -1. So that means I could evaluate tan of negative 45 degrees and realize that it's -1. So when we define each of these new functions that we're going to define here in terms of sine and cosine, basically that means that the simplest way to wrap your mind around them and to actually evaluate some of these other weird looking functions is to evaluate sine and or cosine and then put that together to make the new function value, as we just did here with tangent. All right, so let's look at the other three. These are all 6 primary trigonometric functions. So the CSC theta, that stands for cosecant. And cosecant of theta is just the reciprocal of the sine function, or the flip, or 1 over the sine function. So using what we just did on the for the tangent, let's say I was tasked to find out what is the cosecant of -45 degrees. And so I would say, well, that's 1 over the sine of -45 degrees. So that's 1 over the flip of, and the sine of -45 was -√2 divided by 2. But if that's in the bottom and I have to flip it, well, when I flip it, I get -2 over the square root of 2. And if I even want to go an extra step and rationalize the denominator back from good old algebra 1, which we've all probably forgotten most of, I would multiply that by √2 in the top and the bottom. And these would cancel. Basically, these two together here would become a 2, because the square root of 2 times the square root of 2 is 2. And then that 2 would cancel with that 2. So all I'm left with is -√2. So we can then find values for cosecant by simply finding values for sine and then taking the reciprocal of those values. And of course, you can do that on a calculator as well. You'd like to have a calculator where you can find a cosecant. At the very least, you could find a sine, and then you have a 1 over x button, which would allow you to get the reciprocal of that number. Questions, comments so far with this introduction of some of these other functions based on sine and cosine? So the way this matches up with what the book and the slides showed before is they defined sine as the y value over the r value, and then they defined cosecant as the r value over the y value. They just flipped the two values. But I think we are honestly a little better off by just always focusing on feeling very comfortable determining values for sine and cosine, and then just remembering how you flip them or make a fraction out of them to find the other 4. Questions at all? All right, so then again, in a similar sense, the secant is 1 over the cosine. So if I was trying to find a secant of a theta, I would find cosine of that theta angle, and then I would just flip the answer. And cotangent is just the flip of the tangent. So since tangent was sine over cosine, cotangent is most simply thought of as cosine over sine. Because if I flip sine over cosine, I get cosine over sine. And so again, cotangent, I can find by figuring out what's the cosine, what's the sine, then I make the fraction, cosine over sine. Okay, so with those in place, now we can, by just focusing on evaluating sines and cosines, we could also evaluate any of the 6 basic trigonometric functions by focusing on those first 2 primary ones. So there's show some examples of how we could use that. It says find cosine theta given that secant theta is 5 over 3. Well, secant is the flip of the cosine, And the cosine is the flip of the secant, because you flip one, you get the other, and vice versa. So if they tell me secant is 5/3, then cosine would be the flip of that. And if I flip 5/3, I get 3/5. It's as simple as that. Questions at all about that? So I know these cosine, sine, secant, tangent, I know those all still look uncomfortable. The theta symbol still looks uncomfortable. But we are just going to be using these 6 trigonometric functions, which are based all on sine and cosine for the entire semester. So we will grow our comfort and our understanding of them over time with lots of different problems and stuff. So they have another one here with cosecant, which would be the flip of sine. So they told you cosecant. So if you wanted the sine, you'd flip the cosecant, which they did. And then like I did, they did a rationalization of the denominator like I did in my little example here. Okay, so now we touched on this a little bit before, and now we can do that for all 6 functions. We looked a little bit, or I, on my graph before, looked at these first 2 columns a little bit, and now we can extend that to the other 4 functions as well. So what are they talking about here? Well, just about figuring out the sign of your answer for one of these functions based on looking at which quadrant the angle is in. So we have theta is in quadrant 1, 2, 3, or 4. I should have done this actually on the homework that I was trying to do for you, because I wasn't paying attention to the fact that I should have had a negative value for my my -1. All right. So again, the way to visualize this is just remember that when you have the graphing quadrant system, quadrant 1 is up here, quadrant 2 is there, it's in a counterclockwise direction, quadrant 3 is down here, I drew these in last time, and quadrant 4 is over here. And when you are in quadrant 1, x is positive and y is positive. When you move over to the left on quadrant 2, the y values have stayed positive because you're still above the x number line, but now you're on the left of the y-axis, so the values of x have now become negative, which I forgot a minute ago. When you go down to the 3rd quadrant, you're on the left and below, so both of the values will be negative, all points in that quadrant. And in the 4th quadrant, you have a positive x and a negative y. So since sine and cosine are the x and y values of a point on a unit circle, well, if you look at which quadrant your point is in based on the theta value, then you can immediately see what the sine or cosine would have as whether it's a positive or negative result. So in quadrant 1, this pair of signs matches the fact that x and y are both negative. In quadrant 2, this pair of signs matches over here, that you have a negative and a positive, etc. There's quadrant 3 matching with that pair of sign values. And then quadrant 4 is there, so that's why they're listed. And then to get all 4 other functions, you just make a fraction of these signs. Tangent is sine over cosine. In quadrant 1, that would be a positive divided by a positive, which would give you a positive. Cotangent is cosine over sine. In quadrant 1, that's still positive over positive, so you get a positive. Basically, anytime you make a fraction with only positives, you're going to get a positive. When we go to quadrant 2, then tangent, which is sine over cosine, is a positive divided by a negative, which leads you to a negative result. And if I flip that for the cotangent, then I have the negative divided by the positive, but that's still negative. Secant is 1 over cosine. The cosine is negative in quadrant 2, so 1 over a negative would be negative. Cosecant is 1 over the sine, which is positive in quadrant 2. So that's the only one of those 4 functions that ends up positive when you're in quadrant 2. And you can do that for the other quadrants and the other functions as well. So that's how this chart is created. I'm pointing this out because I never suggest that we memorize charts like this. I just lost my chart. There it is. I never suggest that we memorize charts like this, but that we understand how they're created. Because if you understand how they're created, you don't have to memorize anything here. And again, if you just focus on your sine and your cosine, then all the other 4 functions will result from that. Questions, comments about the signs of function values in the various quadrants? Is that a question for Mr. Hale? I can't see all of you, and you are muted. If you would unmute yourself, you don't mind.
I'm sorry about that.
No
Yes,
problem.
just so I'm following through.
Uh-huh.
If we take the signs like with sin and cos,
Uh-huh.
we add those together and we get a positive tan. And if we were to add the positive signs for cot and sec, we would get the positive sign for C, S, and C.
Yeah, now we're not adding them. We're actually putting them into a fraction, just to make sure that I'm clear about that. Because we defined up here that sine, for example, or tangent, for example, is sine divided by cosine, right?
Okay.
And so if I know for a particular quadrant that the sine value is positive and the cosine value is positive, then how would I use that to figure out the tangent? Well, since tangent is sine divided by cosine, then for the tangent, I would end up taking a positive number and dividing it by a positive number. And so then you can go back to the rules of signed arithmetic, that if you take a positive and divide it by a positive, you get a positive. And that's why tan would have to be positive, because I'm taking one positive number and dividing it by another one. And that will always result in a positive number. Does that make more sense?
Yeah, yes, it does. Okay.
So for secant, let's say I was talking about this one here, the secant in quadrant 2. Well, I want to remember that secant is 1 over cosine. And I know that in quadrant 2, the cosine is negative, right? So the secant will end up being 1 divided by some negative number. And if I take a positive 1 and I divide it by a negative number, I'll end up with a negative number, because positive divided by negative is negative. And that's why for secant, they show that any angle in quadrant 2, you'll end up with a negative answer. Is that helpful? Does that satisfy your answer, or give you a satisfactory answer? Or do you want a follow-up question there? No? Okay. All right, so basically these come from making a fraction for these 4 functions of the signs of what you got for cosine and sine, based on all the fractions that we talked about up here. Tangent is sine over cosine, secant is 1 over cosine, things like that. Okay. All right, so moving on. They kind of summarize that here and just sort of say which ones are positive and negative in each of the quadrants. So they sort of say, well, in quadrant 1, everything's positive, so they're all positive. And then they break it down. But again, I really, much as I understand what they're showing you here, I don't recommend you try to memorize these, because that's just not the best way to learn this. The best way to learn it is to think about the fact that sine and cosine define the other 4. And once you get used to that, then you can calculate all of these possibilities directly with sine and cosine, and you don't have to memorize this table or memorize this table or any of that stuff. It's nice to have a summary of the results, but we don't want to have to try to memorize a bunch of these different results without understanding why they are what they are. How are we doing here? 25 minutes. All right, so in order to see if we got this idea of this summary, they ask us to determine the signs of the trigonometric functions of an angle in standard position with the given measure, and then they give us a measure of the angle. So they're asking us to do it for all 6, but let's just do a couple of examples that would spring from that. So we want to first be able to recognize that the measure of 87 degrees, that's in quadrant 1. And we remember in quadrant 1 that all points are positive, comma, positive, meaning the sine is positive and the cosine is positive. And if the sine and the cosine are positive, then any way you flip those or make fractions, you're going to still get a positive. And so they can conclude all of its trigonometric function values are positive. Now, if I go off to something a little bit different, like 300 degrees, well, you may remember that all the way around is 360. So if I didn't get all the way to 360 and I stopped at 300, I would be 60 degrees before I finished. And that puts me in quadrant 4. You can try to maybe visualize these things a little bit sometimes, right? We have 0 here, we have 180 here. And after you go to 0, you get back to 360. So 300 is going to be down there somewhere. You didn't get all the way around to 360, but definitely that's going to be in quadrant 4. And so points in quadrant 4, points in quadrant 4 have positive x values and negative y values. That means when you're in quadrant 4, sine will be positive. I'm sorry, sine's the y value. I just said it backwards. Cosine will be positive. Sine will be negative. And you can make the other 4 fractions correspondingly. For example, cosecant, which is spelled out here. Cosecant is 1 over sine. And sine is negative, so this would be 1 over a negative. And if you divide a positive 1 by a negative, you get negative answer. And each of these can be figured out with that logic. And I think that logic and thinking through that and getting used to that will serve you well for the entire semester. Questions about that? All right, let's get on to identities because that'll take a little bit of work. So they do some other angle here. Identify the quadrant of an angle. They practice that. And so they also discuss the ranges of these values. So this is a little trickier if you've lost track of your idea when you have a function of what the domain and the range is. I started to talk about that a little bit last time about a function and how if you think about the range of values you can get from the points going up and down, and that I said that the y values would always be less than or equal to 1 and greater than or equal to -1, and that would be true for all the x values. Whenever you have points on the unit circle, you can't get a point on the unit circle that's higher than 1 or more to the right than 1. And that leads us to these range notations. Specifically, sine and cosine are what I discussed last time, and this is their interval notation for the values from -1 to 1. So that makes sense with what we discussed before. However, when you start thinking about flipping these numbers, things get a little bit more complicated. So if I'm flipping a number, like say, let's say we start with secant. Secant is 1 over cosine theta. Well, if have 1 over a number and the number is always between -1 and 1, then I can't have like a half. I can't have a 2 on the bottom. I can't have a fifth. The number on the bottom has to be a small number that's less than 1. So instead I get things like 1 over a half. And if you have 1 over a little fraction like that, it gets flipped and it becomes a bigger number. And so what they're showing here, and of course that could have been a -1/2, which would have led to a -2. And so what they're showing in this range here is that when you flip these little numbers, you get big numbers that could be anywhere from 1 all the way up to infinity. Infinity is not really a number, but as big as you can imagine. If I have 1 over 1/10, well, that becomes 10. So you can have very large numbers when you take values that cosine would have given you and you flip them. Because cosine is going to give you little numbers between -1 and 1. And when you flip those, little numbers flipped turned into big numbers. If I flip 1/20th, I get 20. If I flip 1/10th, I get 10, etc., etc. Now, if I make fractions of any combinations of these numbers, I could get any number I want. So the tangent theta, that's sine divided by cosine, that can give you any number you want. And we're going to go into much more detail about these later when we look at graphs of these functions and things like that. But they do have this initial diagram, and they ask you to begin to think about the ranges of the trigonometric functions. If any of you are already starting to work with a graphing calculator, you can just type sine X into your graphing calculator and have it make a little picture for you so you can visualize the range of the Y values of your graph, if that's helpful at all. Now, we're going to do that a lot more extensively later, but if you're already playing with a calculator, this is a time where you could do that as well. All right, so having said that, they ask for you simply possible or impossible for a particular answer to be produced. And I kind of mentioned this before, specifically with like sines and cosines. That's a good thing to think about. Since both sine and cosine have to be somewhere between -1 and 1, if you ever had a statement that gave you an answer that's bigger than 1 or less than -1, that's not possible. No, can't get that. Think of it this way: the Y value of a point on the unit circle could never be 2.5, because that's just too far away from the origin. That's too high. That's the graphical idea of what's going on. But you could just compare the answers they gave and see if they fall within the ranges that they summarized here to try to answer these kinds of questions if they show up like on a homework problem or practice problem or something like that. All right, so let's look at this next example, finding all function values given one value and the quadrant. So this is a procedural thing to have you begin to work with the trig functions and practice with them. So let's take a look at what they're offering up there. Suppose that angle theta, when they put this symbol, that means they didn't have the graphic there, I guess, that a particular angle is in quadrant 2, and we know that sine of that angle is 2/3. Find the values of the other 5 trigonometric functions. All right, so we're in quadrant 2. So what does that tell us? Well, we're in quadrant 2. All points in quadrant 2 have a negative x value and a positive y value. And we can see that the y value is positive because the y value is 2/3, because sine of theta is 2/3. And so we then want to say, how could we figure out the other values? So starting with trying to figure out the cosine, we could imagine that we have some point in quadrant 2 on the unit circle where the y value is 2/3. So if I draw some point here, and I just imagine that the y value is 2/3, that means that the height of this side of this triangle is 2/3. That's the y value. I know that the, oops, on the unit circle that the diagonal is a 1. And that over here, that means that this x value is the only unknown side in this right triangle. And we can use the Pythagorean theorem to figure that out. Now they're kind of going back to their original definition, which is fine too. I would do it slightly differently. So I'm just going to show you what I would do. So then I would say that 2/3 squared plus the x value squared is equal to 1 squared. A squared plus b squared equals c squared in the Pythagorean theorem. We know the y value is 2/3. We know the angular hypotenuse there is 1 because it's a unit circle. And we know that the x value is the thing we're supposed to figure out because I'm trying to find out what's cosine theta. So that means I can solve this. 2/3 squared is 4/9. So I would subtract 4/9 from both sides. 1 squared is 1, so I end up with x squared is equal to 5/9. And then I would square root both sides, only taking the positive since it's a side. And I would get that x is the square root of 5 over the square root of 9, which is 3. I said 5 and then I wrote a 4. I sometimes, my brain doesn't do it with my hands thinking or something. So square root of 5 over 3. So what that then tells me is that cosine of that angle would be the square root of 5 over 3. And because it's in quadrant 1, I know that's going to come out to be negative. I'm sorry, quadrant 2, because all the cosines are negative here, negative. So we use a little right triangle to figure out how big the missing side is, and we use which quadrant the angle is to tell us what sine would be of that coordinate. So I'd have an x value of negative 5 root 5 over 3. So that would be the cosine of that angle. And so they arrive at that here. So they did it slightly different way. You could do it that way as well. But the way I just showed it ends up with the same answer. And then as I described before, once you know the cosine and the sine of an angle, you can use those values to figure out any of the other 4 trigonometric function formulas by just making fractions. So for tangent, then you could take the sine value divided by the cosine value, et cetera, cotangent, cosecant, et cetera. All right, so let's finish up now with what do we got here? Yeah, a little over 10 minutes. So we can look at Pythagorean identities. So because of the way sine and cosine are defined, we can create equations that relate these function values together. So for example, I defined sine and cosine as the x and the y values of a point when the unit circle. So by the Pythagorean theorem, we know that x squared plus y squared equals 1 squared. And the x is the cosine value and the y is the sine value. So that gives us our first Pythagorean identity. That if I take the squares of the cosine and sine values and add them up, I get 1. And we're going to use this identity a lot for the whole semester. This is the #1 identity, and usually anyone that somehow gets out of the end of a trig class, they remember this probably close to the rest of their life. That's how much we use this and how important it is for this topic. So that means if you ever had a function that had sine squared plus cosine squared in it, that whole part would simplify to just becoming a 1. Then they have 2 more identities, which we could try to justify graphically or with a picture. But I think the best way for me to illustrate those is to show how you get those if you take the first one that we just got and modify it a little bit. Again, I think we're going to have the most success in trig by thinking of everything back to sine and cosine. So for example, what is tan squared? Tan squared would be sine over cosine squared. So tan squared is the same as sine squared over cosine squared. Well, notice that that's right below the identity above that has a sine squared in it. So if I wanted that first term in the first identity to become a tan squared, I would divide it by cosine squared. So basically, I'm going to take everything on both sides of the first equation and divide them all by cosine squared. And if I divide everything there on both sides by cosine squared, we can do the same thing to both sides of an equation. Well, then sine squared over cosine squared becomes tan squared. Cosine squared divided by cosine squared becomes 1. And 1 over cosine squared is the definition that would give us secant squared. Similarly, if I take the first equation and I divide everything by sine squared, then I get this one. Because sine squared divided by sine squared would give me 1. Cosine squared divided by sine squared would give me cotangent. And 1 squared divided by sine squared would give me cosecant. So the second two identities you can directly get from the first identity by taking everything in the first identity and either dividing by cosine squared or dividing by sine squared. And then you get the other identities. All right, so these are just, what is an identity used for? What does this equation help us do? We want to see how does this allow us to solve problems? Well, the quotient identities are basically the way I told you to define these functions in the first place. But let's see how they would want us to do a problem using this fact. Find sine and tan given that cosine is equal to this value and sine is greater than or equal to 0. All right, well, we know that there's a relationship between cosine and sine, namely their squares add up to 1. So if you know either one of those, you could find the other. This is basically just using the Pythagorean theorem. So we start with the fact that sine squared plus cosine squared equals 1. We now were given the cosine, so we plug that in to the cosine. And that gives us an equation where all we don't know is sine, and then we can solve for sine, which they do here. And because we're told sine is positive, we can then choose the positive square root and get an answer for what the sine must have been. You can do the same thing with the other pairs. So let's look at what these would allow us to do. This first equation that has the sines and the cosines in it means that if they give you the cosine and you know at least the sine of the other one, the quadrant that it's in, then you can figure out the sine. Similarly, if they give you the tangent, you could figure out the secant. If they give you the cotangent, you could figure out the cosecant, because these show up as pairs in these identities. And when that happens, if they give you one of the pairs, as they illustrated in example 6, then you can solve for the other one you don't know. So while we have this example in front of us, does anybody want to ask a question about any part of that or what they did here? There is some solving, there is some algebra here. If the algebra is still feeling uncomfortable, that's a very common experience. And if it's really holding you back from following along with what's going on here, I will point out that the first chapter, or the one before chapter 1 in the book, the first 100 pages does have algebra review in it. And it could be that you might want to go back and try doing some algebra review from some of those problems if you're really feeling that's holding you back. We don't really have time to go over that in detail in our class. As you saw from the syllabus, our semester is filled just covering with the trigonometric new material. but it doesn't mean if you have some extra time that you might not get some benefit from going and doing some review there. And I can always answer questions about that as well. So here's example 6. And in this case, they use the tangent. It says find tan theta, use the quotient identity, in which they use the values that they had above that you just determined, and they just made a fraction out of them. And I've already demonstrated that we could do that. If you know sine and cosine, you just make the fraction and that tells you the tangent. And I think, honestly, that's the best way to find tangent by hand if you're not using a calculator, is to just find a sine and cosine and then make the fraction. So this identity definitely pushes us in that direction. Now it says there is a caution here. Be careful to choose the correct sign when square roots are taken. So we saw that in that first example here, where they said they had to tell us right here, they had to tell us right here what the sign of the answer should be, because cosine can have a negative 3/4/4 value in a couple different quadrants. That's just the x value. So that could happen in quadrant 2 or in quadrant 3, that you get that kind of an x value. And in quadrant 2, sine would be positive, and in quadrant 3, sine would be negative. So they had to clarify for us that the sign was positive here, and that's how we chose the positive square root at the end of the problem. And that's what this caution is about here. Be careful to choose the correct sign when square roots are taken. All right, let's see what happens next as we have our last few minutes of class to take one more little step forward. Using the identities to find function values. So it says find sine and cosine given the tangent is 4/3 and theta is in quadrant 3. So there's a couple of ways we could think about that, but we know that tangent is equal to sine over cosine. So they take that fact and they make a little equation here. And if you know sine over cosine is 4/3, and you know you're in quadrant 3 where they're both negative, then you could say, all right, well, I need to come up with values that would have that ratio. So how do I get values with that ratio? Remember, sine and cosine themselves are numbers between 1 and -1. So they showed the other way to do that instead is to focus on the identity where you had the sine and the secant here, because the secant is just the flip of cosine. So if you use this to solve for secant, and they demonstrate that here, I'd go through it with you, but we're almost out of time. Well, then you can figure out what the secant is, and then you can just flip that to see what the cosine is. You'd still need to use the fact that it's in quadrant 3 to tell you that it's a negative, which they chose here. But example 7 will help you take a look at that. And again, you can always go back to these slides, which we had to rush through a little bit in these Zoom sessions, and scour through them in a little more detail because they're available in the multimedia library. Or of course, you could go to the textbook where they take these exact same ideas and flesh it out a little bit more fully. But in this case, their example 7 illustrates how you could use the tan and use that to come up with the sine and the cosine. I think they complete it on the next slide to get the sine as well. So that's a good example as well. All right, and that's just leaving a couple minutes left. So we're going to stop there. Let me stop the share.